Welcome to video number 31 in the Foundations of the Computational Economics course. In the previous video we solved the cake eating problem on the grid, which was motivated by trying to avoid the need to interpolate a value function in the next time period. And so we saw that the solution produced by that approach was very inaccurate. Now, in order to do a better job on solving the cake eating problem, in this video we will look specifically at how to approximate functions in Python. So first, let's look at the interpolation problem. Imagine that we have some function of interest, f of x, and it's hard to compute. We don't want to recompute this function at every particular point of x. Instead, we have already computed this f of x in a collection of points, which I just write as x1 to xn here. So we have these values for this function f. The point is that we should be able now from this data to compute the f of x at any points within the boundaries between x1 and xn. And you can already sort of notice that this x1 and xn play an important role as the boundaries for the interval where we want to be able to compute f of x. And this is related to the interpolation term. In the extrapolation case, we may have to somehow come up with the values outside of those boundaries. Okay, so there are two approaches. The piecewise approach, and that's basically from the dots, which are the function values distributed somehow in the space. We can work with this, somehow independently and connect the dots. That's what I call by connecting the dots. What functional form to use for the connections for each of the segments? What are the advantages and disadvantages of this approach? You can think of some already. Now, the other approach is to use a similar function s of x, a completely different one, and probably an analytic function, so it's easy to compute, to represent f of x between the data points. Again, which simpler function? What functional form? And usually polynomials is a straightforward choice. What data should be used? By data here, I mean the collection of the points f and computed f of the collection of the points x's and the function computed in those points. And of course, the central question of all of this is the accuracy of the approximation, and we'll look at that. Now, there are some terms around these tasks which are used sometimes interchangeably, but let's try to separate them. So we will be talking about function approximation, and that would be equivalent to interpolation. This is the case where the data, functional values of the collection of points is matched exactly. So this is essentially the connect the dots case, or it could be that we come up with an approximating function such that it is exactly equal to the function of interest in all of those points. On the other hand, we will have curve fitting problem, and this is more of a statistical problem. In nonlinear and linear regressions, you're trying to fit a particular function to describe the central tendency in the data. So the difference, the fundamental difference here is that in the second case, we assume that the data has noise, right? So the data that we observe may be a little bit higher, a little bit lower than the function or the functional value that we're interested in. That's the fundamental difference from the first case, where we want to match exactly the function values at the points of the grid. Now, it could be that if the model is over-identified, so if we're trying to find a polynomial with more degrees of freedom than the data points that we have, I'm sorry, the less number degrees of freedom than the points that we have. So we have more data as needed to identify all of the parameters of the simplified function. Then we will sort of get into the domain of curve fitting. Just because of that. And here, this is where the approximation sort of links a little bit to the curve fitting too. So we're approximating a function of interest, but if we have too many dates, too many points where it's already calculated, then we're technically fitting a curve, although the task is to interpolate. All right. Now, extrapolation is the case which I already mentioned, and this is computing the approximated function outside of the original data interval. This is hard and should be avoided in general. Sometimes it is possible to derive theoretical properties of the function of interest, or f of x, which give rise to our ability to extrapolate with a decent degree of robustness in the area where we don't have any data, any functional values calculated there. But this should be done with extreme caution, and it's always better to try to widen the interval where the function is calculated. Where the grid lies, right? The wider boundaries for the grid to try to avoid extrapolation. Okay, so let's look at the first case of the piecewise approach to function interpolation. And this is what's commonly referred to as spline interpolation, where spline is simply a curve composed of independent pieces. Okay, and so the simplest spline is just straight line segments connecting the dots of the function. But a more general definition is the spline is a function which is defined on a closed interval. And we will have the order of the spline and the degree of the spline, which are different by one and cause some confusion. But what is this function s of x? Well, it has to have a number of smooth derivatives, the number being n minus 2. So the 1 less than the degree of the spline, or 2 less than the order of the spline on the given interval. And between the given the grid, the collection of these knot points, the function s of x is a polynomial of a degree n by 1 on each of the intervals. So that's the definition. The spline is a piecewise polynomial function which maintains a certain degree of smoothness. Let's see how it can be implemented using the example of cubic splines. So cubic splines refer to the case where the order is 4 and the degree is 3, thus cubic. The functional form for s of x will be the third degree polynomial on each of the sub-intervals defined by the grid. And how do we find all of this, many coefficients? Let's count them first of all. So we have 4 coefficients for each of the intervals, and the grid is here starts from index 0 and goes all the way to n. So there will be n sections and intervals on this grid. So altogether we will have 4 times n of these unknown parameters. Now, 2n equations come from the fact that each segment has to pass through its interval points. So each of this function has to be defined and equal to a particular point on the left and on the right. And again, because there are n subintervals, there are 2n equations to ensure that. Now, for the smoothness conditions, and remember now the n is 4, so we have to have 2 smooth derivatives for the cubic splines. And so there will be 2 times the number of points where 2 different segments of the spline come together. These are the points where we have to ensure the smoothness of 2 derivatives. And how many points are there where 2 different segments of the spline come together? Well, 1 less than the number of intervals, right? So there will be 2 n-1 equations to ensure that 2 continuous derivatives at each interior point of this spline. And that leaves us with 2 equations which we still have to find in order to determine all of the 4 unknown coefficients. And here there are some options. So there are a couple of options here. Either that the second derivative is set to 0 for natural splines, or that the first derivative is set to particular values for this secant Hermite type of spline. But this is how it's possible to determine a large number of coefficients to connect the dots in a particular way. So let's look at how it's going to be done in Python. And here we will not be coding this segments from scratch. We will rely on the standard scientific libraries in Python. This will be a sub module of NumPy, and I'd like to make pictures, of course. Now let's here we haven't talked fundamentally about the random number generators. It's coming in a couple of videos, but this line here just fixes the random number generation at a particular generator at a particular state, so that we can have repeated pseudo-random numbers to get the same cases every time we run it. Every time we run the code, so that we can see the changes in the interpolation approaches rather than changes that are caused by this realization of the random numbers. So what do I need the random numbers for? Well, I want to generate a grid, a collection of points in X, and these are going to be just uniformly distributed between -5 and 10, and we'll have 12 points. We want to sort them so that we have a sorted set of points. And in parallel to that, I'll have a regular grid, which is called XR here, and this is just a linspace, right? So the 12 points distributed regularly at equal intervals between -5 and 10. And here's the function that will work throughout this video to try to interpolate. You can see that this is the exponent times the sign, so it's going to be a somewhat periodic function. And there's this additional component, which is the inverse of the 1 plus x square. That'll go. This is not a very simple function to work with. And we'll see differences between different approaches to interpolation or function approximation. Let me not go through the details of this plotting function. Its function, its performance will be obvious when we use it. So first of all, here is well, let me go back to the plotting function, actually. So this is the function that we want to interpolate. And as you can see, by default, it's set to the function that we just defined. Okay. If we want to look at a particular set of points in this function, then we'll have to do something extra. But so far, it's just going to default to the function that I just defined in the previous cell. And so this will produce the plot of the true function. Now this non is the first argument, refers to the interpolation function that we don't want to plot yet. So here's the function that we will need to interpolate. And as you can see, the dots, the red dots, they show the location of the grid points where this function will, or we assume, we already have computed. So we know the functional value there. All right, so first let's import the interpolate module from SciPy. And there's a method there, the function which is called enter P1D. So this is a one-dimensional interpolation. That's probably the easiest case. It's one-dimensional linear interpolation. It's probably the easiest case and the easiest one to run. Just like that. What do we have to give to this function? Well, it's the data, the axis, and the functional values computed at the axis. So this is the data which is used for interpolation. This call here produces an object, a callable object, which is the interpolation function itself. And now we can call this fi of different values. You know, fi of 0 or fi of of 0.5 and so forth. Instead, we're just going to give this fi as a function to our plotting routine to get a picture like this. In gray, again, is the function that we wanted to interpolate, and the interpolation is going to be computed according to this blue line. And as you can see, in the simplest case, this is literally connecting the dots with straight lines. You know, because we didn't have any information about the functional value in this region here, we are missing quite a lot, right? And so the error from the interpolation, this distance between the approximating, the interpolating segment and the function itself is kind of high. Well, that's because of the location of the dots. If we look at the regular case here, I have to give to the plotting function this regular case as well to get the dots. So in the regular grid, where the dots are distributed uniformly across the interval where we want to look at it, you can see that the linear interpolation is performing a lot better, although it does not have any means of replicating the curves of the original function. So it's only the increasing the number of dots that would increase the quality, the accuracy of this interpolation. So let's look at the help here of this function. Well, you can see that this is a class to interpolate one-dimensional functions, one-dimensional interpolation. What are important things to note here? Well, this x and y are the data for the interpolation. We can have we have an option to choose the kind of the interpolation. So. Which can be a whole lot of different things, and linear and nearest zero, quadratic and cubic for splines, and S-linear, which is, I believe, the same thing as linear. We'll look at them in a moment. Now, various technical arguments, and this is the important one, bounds error. So if true, the value error is raised when extrapolation is attempted. Okay, we will see that extrapolation is really where loss of accuracy is really possible, and therefore you have to be very conscious of the fact that you are extrapolating, and thus this routine in SciPy by default will raise the error, and only if false, okay, then the out of bounds values are assigned to something else. And what's the fill value? What are the possible assignments? Well, it could be assigned to a particular value, or it could be assigned to a value, one for below and one for above, the boundaries of the interpolation interval, or it could be extrapolated. And extrapolation is essentially using the last segment of the spline to produce values for the outside of the interval. Okay, let's see how we can change the kind of interpolation. So this here is linear, or S-linear is the same. But we can use splines that we've talked about just as well. Okay, before going there, let's look at this interesting previous, next, and nearest neighbor nearest stands for nearest neighbor type of interpolation. So here you can see that the previous value is used all the way until the next dot, and this is the stepwise approximation that results from this approach, or from this type of interpolation. This is still an interpolation, although kind of funny. I've only seen it used in theoretical derivations. And same thing with next. It is really easy to compute, though, right? So that's the beauty of it. The nearest neighbor is, you can see the steps are made exactly in between of the neighboring grid points. Okay, something which is more often used are the linear or S-linear, linear splines, quadratic splines, and the cubic splines. So these are the interpolations which are good choice for the smooth functions, like the one we have here. Right, and you can see that the quadratic and the cubic, the higher order splines, they are doing a much better job in replicating the function. Although already here it's kind of obvious that the cubic spline and quadratic spline are having some trouble over here, right? So the quadratic one is almost linear and the cubic one is going too high up. And why are they doing this? Well, they are matching the derivatives here. Remember, around this point the derivative has to be continuous, 1 or 2 for the cubic case. Okay, so when doing interpolation or a function approximation in general, the key question is how accurate is that approximation. And so we can check the accuracy by simply comparing the interpolated values to the actual values. This is what's done here for the linear, quadratic, and cubic splines. First, we create the interpolant function, and then for the xd, which is a really dense grid on the same interval, we're computing the absolute difference between the functional value and the interpolated value at the same point. And then we're just plotting this. And as you can see, I believe the colors are the same. So magenta is linear. The linear interpolation for this particular function is not performing very well, although at some intervals it's actually better than the cubic one, which is green. And quadratic one is probably the best of the both worlds, although it's kind of hard to tell whether it's a general solution or not. Let's look at the same plot for the regular grid. You can see the difference here is that the points of the grid which we used for creating the interpolation function, they were spaced irregularly here, and they are spaced at the same interval lengths in this picture. So the only difference is that now I'm using the XR as the grid to create the interpolation function fi. And you can see here that there is a significant difference between these two graphs. So first of all, it's the magnitude, right? So the highest, the max error is 1.05 here. It's only 0.46 in this case. So regular grids are actually helping us. But what about the ranking of different approaches? Well, cubic is not doing really well at some of these intervals, whereas here it seems that cubic is at least as good as quadratic, so probably the best in this particular approach. So, thinking about the accuracy of interpolation, we have to consider several factors, and in fact, how to reduce the approximation errors. Take a moment to think about that. All right. So as we just talked about, the type of interpolation or the location of the nodes, right? That's what we talked about just now, where regular is appearing to be a better choice than the irregular locations for the grid points. Now, of course, I guess many of you thought about the number of nodes. As you increase the number of nodes that are used to create the interpolation function, then the accuracy should increase as well. And that's actually the case. The cost, of course, is that if the function of interest is hard to compute, it could be, some computation from an economic model. Then it is just costly, and then we have to trade accuracy to the speed of the overall program. And then, of course, the interpolation type, which is a bit of art, but you can remember that matching the function of interest and the functional form and the theoretical properties to the interpolation method, that's the key to get good interpolation results. Okay, so let's now turn to the second type of interpolation, where we're looking for a simpler function g of x to represent f of x. And by simpler, I of course mean that it's easy to calculate. So we will focus particularly on the polynomial approximations. So g will be a polynomial. As before, we have a data set composed of n plus 1 points indexed from 0 to n. And the functional form is going to be a polynomial, as I said, of degree n. So if we have a degree n polynomial, it has n plus 1 parameters, coefficients. That means that n plus 1 points will be enough to identify all of them. Just enough, I should say. And that's what it says here. So if xi's are distinct, so they're all different, then the coefficients of polynomial are uniquely identified. Okay, so let's now think what happens if we add more points. Before, adding more points meant that we would have a more accurate representation in the spline case. Does it hold with the polynomial approximation? Let's see. Let's start by looking at how you actually do it. So the polynomial is a submodule in NumPy, and I'm going to import it separately under the name of polynomial. And so then we can say that, the degree of polynomial that we want to get that identification is the length of the x vector minus 1. And we will call this function to create a polynomial object p that we can then evaluate. How do we create it? Well, we create it from the data, from the axis and the functional values in those axes, and the degree is going to be corresponding to the number of points in the way that I already announced. Now, the interpolation function will be the function that evaluates the polynomial p in the points x, and I'm creating this function separately with the lambda. Okay, and then we can feed it to our plotting instruction, and what do we see here? Well, it's kind of hard to see, right? All of the function is looking like just a line now, with the polynomial, the approximating polynomial. That's the blue line. It's going sort of way off the scale here. Okay, let's see what's happening. Let's look at the irregular grid first, right? So the points here are not spaced equally over the interval. And that's actually the reason why we have this blowout in the polynomial approximation. With the regular spaced points, as you can see, it's more sensible, right? So we can see that now the points marked here in red, they are all regularly spaced across the x dimension. We have the functional values and the polynomial, which sort of repeats the function that we're interested in this middle section here, but then starts doing something strange, especially over here. Why does it sort of want to go down here? That's essentially one of the problems with polynomials, is that when we force the polynomial to go exactly through the points, then we don't actually have a complete assurance that it's not going to do funny things like this, especially towards the end of the intervals. Let's explore a little bit further. So here I have a loop where n is going to be changing. That's the number of points, and I'm repopulating the x grid called here x2 with a given number of points, right? And then this letter, that's going to be a color of the line, so we can compare different lines, different approximations. The body of the loop has all the same functions, so we are approximating with polynomial the function calculated now in the new set of grid points, and we'll plot. So what do we have here? With 5 points, the approximation is quite poor. So it's still the polynomial approximation, right? The approximating polynomial goes through all of the points that we've calculated on the function of interest. It's going to be value function later. But you can see that even the general shape is not really repeated well. Let's go to 10 points, and you can see now that in the middle here, the approximation is pretty reasonable. Again, it does something sort of unexpected in the ends of the intervals, but other than that, it's looking promising. Now 15 points, and you can see that the approximation in the middle of the interval is even better, but towards the end we have this blowout. The polynomial just jumps to some unreasonable level. What about 25 points? Again, the line of interest looks almost flat. That's because we are really off the scale with this jumps. The conclusion that we have to make here is that by increasing the number of points in this polynomial approximation, we are actually not necessarily increasing the accuracy of the function approximation when it's approximated with polynomials, and that's actually the case. Okay, let's look at how location of the points of the nodes affects the polynomial approximation. And here we have a loop again, but now the loop inside of the loop we are sort of perturbing the points of the grid by adding a random component to them, and as you can see, it's a small fraction of the interval. They're allowed to wiggle between -1 and 1 a little bit, and then we approximate with polynomial again, creating the approximating function and plotting it. So the number of points is going to be 8 everywhere, but let's look at the differences of this picture. And you can see here that the problem lies in the beginning of the interval. The approximating function goes really low in this area between -5 and -2. What about now? Now it goes really high up. Remember, we've moved the points. So if you look at the red points collection of points here and here, they are slightly different. But again, these differences are not too large. And yet another case. So these are 3 cases where, even though the locations of the nodes didn't change much, the approximating polynomial actually turned out to be not as stable at the end, but quite okay in the middle, actually, on all of these pictures. What about changing the degree of the polynomial? So in here we have to talk about what actually this polyfit function, what is it doing? So if I keep the number of points fixed, but I change the degree of polynomial, let's look at the picture here. The number of points is the same, but now you can see that, what is it though? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 points. And the degree of the polynomial, so there's going to be 11th degree of the polynomial. So it goes through all of the points. So this is just the case that we looked at here, right? This case here. Just that case there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, okay, that's correct. So 12 points on the grid, and the 11th degree polynomial is then matching the points exactly, or it goes through all of these points, the magenta line. If we decrease the number of the degree of the approximating polynomial, then it is unable to match all of the points, and then the polyfit function minimizes the sum of squared residuals at the points. So this is a least square approximation. And this is the picture that we're seeing here. We are now in the realm of curve fitting, in a sense. So we're fitting a polynomial to this given data. And not necessarily it goes through all of the data points, but it approximates the function of interest rather well. Except maybe the some instability here. But as you can see, the 11th degree is blowing out a little bit, and then the 7th degree is probably not enough. But the 9th degree is probably doing the best job here. It overshoots a little bit on this left end, but it doesn't blow out as much on the right end. Well, unfortunately, this is not going to be easy to say up front. What's really the informative part is that you cannot rely blindly on the polynomial approximation. It would be better to have some sort of a theory to try to minimize this effect of the polynomial going out of control. Okay, so what is a possible approach to for such a theory? Well, maybe we can consider, for the same data as before, consider any functional form from some class, right? From some class G. And let's find an arg minimum. So let's minimize this measure. Maybe it's a square residual measured somehow between these two functions. And I'm not saying how yet, but maybe it's a minimization of the squared error, the squared distance between the functions. That's what we could take as an approximating function. Well, this is a fruitful approach, and now we have to discuss, how do we measure the distance between functions. So let's first define what's orthogonality in polynomials. Consider polynomials over some domain. This can be thought as just a closed interval. And we need a weighting function, which is just some function of x defined over the same domain, which is positive. The inner product of two polynomials is going to be defined like this. So we're taking the product for each x and multiply it by the weighting function as well, and take the integral over the whole domain. This is the inner product defined over the polynomials. Now, the phi I is the family of orthogonal polynomials. If for every pair of orthogonal polynomials, the inner product, which are not the same, the inner product is equal to 0. So this is just the definition. And now let's look at the best polynomial approximation in L2 norm. The L2 norm is akin the distance in the Euclidean space. So the distance between two functional forms, this subscript 2 means that it's that we are talking about the Euclidean, the L2 norm. This is going to be this norm here, okay, that's what I want to talk about. This norm is going to be given by this expression. So we're taking the square root of the squared residuals between the two functions where the residuals are integrated over the domain of the polynomials. So in this sense, in the sense of the best L2 norm, the polynomial p will be the best approximation if it achieves the infimum, the minimum, over all of the possible polynomials in this measure. Now, the result that we have says that P is the best approximating polynomial from this point of view, if and only if the residuals from the approximation, which is the difference between f and p, are orthogonal to all polynomials that we've considered in the class that we've considered. What does it mean? So imagine that in the space of polynomials there's some basis set of polynomials, and then this is becoming linear algebra essentially. So if there's a basis in this space, then the residual has to be perpendicular, orthogonal to every element of the basis, and thus to all of the polynomials in that space. And that means that we are basically projecting, right? This P is the we essentially the residual is what's left after we've projected the function f onto the space of polynomials in the orthogonal way. Okay, this is the theory behind the best polynomials in this sense, in the L2 norm, but we might be more interested in the uniform norm. What's that? That's basically just the difference between the function values, right? So for every x, you can compare x and g, the approximating function, take the absolute difference there, and then take a maximum or supremum over the domain of these functions. That's what's called the infinity norm or subnorm, and this is the limit of the L2 norm when the index there goes to infinity. That's the name. But really what it is just the maximum difference between the two functions. And that's what we might actually be interested in, thinking about this blowouts, the unreasonable increases of the approximating polynomial over the function of interest. Okay, can we achieve the best polynomial approximation in this subnorm? Can we find the way to compute this p, the approximating polynomial, which would achieve the infimum, the minimum distance in the sense of this infinity norm? Okay, so it would be the inf sub or the min max approximation. That's the name here. So it minimizes the maximum difference between the function of interest and the approximating function. Well, this problem was actually proven by Pafnuty, Lvovich, Chebyshev in Russia in the 19th century. And for that, we need to look at what's called the Chebyshev polynomials. They're defined on the -1 to 1 closed interval. The weighting function is going to be the 1 over 1 minus x square square root. Okay? The polynomials are given with these trigonometric functions, but there are recursive formulas as well, which allow them to be computed quite conveniently. And then there's this result. So if the we can construct the interpolating polynomial of degree n using Chebyshev polynomials themselves, such that there is an upper bound on the infinity norm of this approximation. Now, the function of interest has to be smooth enough, right? So it has to have smooth continuous derivatives of the order up to k, and that k actually enters into the upper bound of the approximation. The point is that this scheme achieves the best polynomial approximation in the uniform norm. So it solves the problem of minimizing the difference, the absolute difference between the function of interest and the approximating polynomial. And this is a very well developed technique that is readily available. Now you may wonder why the interval here is just between -1 and 1, But then, of course, the simple change of variables in a linear way with y and x allows us to transfer it to any closed interval a to b. Okay, so here's an algorithm for Chebyshev approximation. We have to compute the Chebyshev interpolation nodes, and this is the key. So the power of the Chebyshev approximation is that it's not only the, for a given degree of polynomial, it's not only the polynomial that we're choosing to approximate this function. We are also optimally choosing the location of the nodes on this closed interval where the function of interest has to be computed for the approximation to work. Then we can adjust these nodes to our given interval. We have to evaluate f, the function of interest at those nodes, and then compute the Chebyshev coefficients in this simple way. Okay, where g is the Chebyshev polynomials, and then we have this. And then we have this approximation, which is just the linear combination of known polynomials of x. And as I said, this is all done automatically in Python in this little code. So we have to import the Chebyshev module, which is also sort of a sub-module of NumPy. And I'm going to do the same loop as I did before with the least square fitted polynomials. But now we're using this Chebyshev interpolation. And observe how this is being used. So this does not require the lambda function in addition. So this is like a normal interpolation routine that we had in the beginning. Right, so the fi is going to be the interpolating function. And let me run this. You can see that with the same degrees of polynomials, 7, 9, and 11, the Chebyshev scheme allows you to have the polynomials which are also very close to the function of interest, and they never really deviate very far from the function that we are interpolating. Compare that picture to this picture here. So there is nothing like this blowouts over here and over here. Everything is really close to the approximating to the function that we are approximating. Now also observe that there are no red dots, so I've removed the red dots. The reason for that is that the nodes of the Chebyshev approximations are endogenous in some sense. They are calculated together with the approximating polynomial. So this is a really good scheme for smooth functions. Now, just to mention, in here we only talked about one-dimensional interpolation. In multiple dimensions, things are much more complicated. So on one hand, there are multidimensional generalizations of all of the methods that we've considered, that I've talked about, but they require quite a lot of computational resources, the main reason of which is the curse of dimensionality in the number of interpolation points when the number of dimensions increase. So it's okay to use it in 2, 3, maybe 4 dimensions, but beyond that, this is going to be just too computationally intensive. For higher dimensions, the sparse approach, small arc grids, which sort of which solve the curse of dimensionality problem with the number of interpolating points, that's useful. And then adaptive grids developed or introduced recently to economics is also a very powerful approach there. Now, it's worth saying that if the grid is for some reasons irregular, like we've considered here in one dimension, in multiple dimension, that becomes kind of a nightmare because the general case requires what's called a triangulation, and that's very intensive computationally. But if you make a jump to a very high dimensional space, then machine learning is a promising approximation technique that is also being used more and more in economics. Okay, here are some additional resources, including this wonderful thesis on Chebyshev approximation that you can look at to understand more about that approach. Okay, see you next time.